I'm Ryan Urbanowitz, and this is part 5 of Machine Learning Essentials for Biomedical Data Science. In this video, we're going to start taking a closer look at how some specific machine learning modeling algorithms work, beginning with a decision tree algorithm. Then we'll build upon what we've learned to examine a variety of other popular tree-based algorithms. Here's a quick reminder of the parts making up this video series. In the last video, we covered the conceptual elements involved in machine learning modeling. Recall this overview of supervised machine learning algorithms that can be applied to modeling on labeled data, where we grouped similar or related algorithms together. Again, in this video, we'll be focused first on the decision tree algorithm, of which there have been a number of implementation variations, including CART, ID3, C4.5, and M5, among others. While we won't get into the specifics of how these individual variations work, we'll be covering the fundamentals of how decision trees work and how these models are trained. Next, we'll go beyond individual decision trees and look at several tree-based algorithms that utilize tree ensembles. Along the way, we'll learn about key concepts such as bagging, boosting, gradient boosting, and gradient descent that can be very useful in understanding both ensemble algorithms and other non-tree-based algorithms. So let's dive into decision trees. It's worth noting that we can think about and define decision trees in two ways. The first is as a decision support tool, which is simply a knowledge representation framework that presents information to facilitate decision-making. Consider this example, where we want to decide what resource to use in making a home repair. At the top of the tree, we ask, does it move? If it doesn't, then we ask, should it? And if so, we want to use WD-40. And if not, there's no problem. Alternatively, if we answered yes to does it move, and no to should it, then we'd want to use duct tape in this case. As a decision support tool, decision trees like this simply lay out the decision-making process based on existing knowledge. Differently, the term decision tree also refers to a supervised machine learning algorithm that learns from data and trains a model that can be used to make decisions and/or predictions. Here on the right, we have a decision tree trained on patients who tested positive for COVID-19, and we're trying to predict which patients will be survivors versus non-survivors. And in this model, 3 features were found to help make this classification. LDH, which stands for lactic dehydrogenase, NLR, or neutrophil to lymphocyte ratio, and CRP, which is a C-reactive protein. In the following slides, I'm going to show you how trees like this work and how they're trained. As a starting point, let's review the terminology used in decision tree algorithms. Here on the right, we can see the basic architecture of a simple decision tree, comprised of nodes and branches connecting to nodes. The top of the tree is referred to as the root node. This is the starting point of the tree, where all instances start during training or when applying the model to make predictions on new data points. Below this root node, instances will subsequently get divided into sets, ideally with a more homogeneous outcome. Next, we have the term decision node. This refers to a node, including the root node, that splits into further subnodes below it. Decision nodes are also referred to as sub, internal, split, or chance nodes. Also, we have the term leaf node, which refers to any node that doesn't split any further. These are also the points at which the outcome predictions are made on instances using the tree as a model. Leaf nodes are also referred to as terminal or outcome nodes. Let's also cover some other useful decision tree terms. First, we have the terms parent nodes and offspring nodes, where parent nodes refer to those that split into offspring nodes below it. So for example, this might be a parent node to these offspring nodes, and this might be a parent node to these offspring nodes. Notably, these offspring nodes can be either decision or leaf nodes. Next, we have splitting, which refers to the process of instances in a parent node being further split into offspring nodes directly below it. For example, splitting might happen here, or here, or here. Then we have the terms branch and subtree, which simply refers to some subsection of the overall tree. For example, the subsection highlighted by this dotted line box. And lastly, we have the terms level and depth that refer to the level in the tree at or below the root node. And we can see these levels labeled here on the far right. This number also identifies the number of splits in the tree that occurs before coming to a prediction. Let's point out right away that one of the greatest strengths of a decision tree is that it's one of the very few algorithms that generates models that can be described as being truly interpretable. So let's explore this a bit further before moving on. As mentioned in the last video, truly interpretable models can typically be expressed as conditional rule expressions, also known as implications from the field of logic. And indeed, decision trees can easily be linearized into decision rules. Each rule will capture a unique path from the root node to one of the leaf nodes in the tree. And the outcome of each respective rule will be the prediction found at the leaf node in the path through the tree that was followed. Here we have the format of a typical conditional rule expression, also known as an if-then expression, where the conditions are identified after the if, and these conditions are connected by ands, and then the predicted outcome follows the then part of the rule. On the right, we have another simple decision tree example, in this case, deciding what to do based on the weather. Let's look at a couple of rules that can be linearized from this tree. Starting at the root node, we have, is it raining? If the answer is no, then we have our decision, don't bring anything. This is the shortest branch in our tree. Or instead, if it's raining, yes, and is it windy, no, then we have the decision, use an umbrella. And we can see these two rules here. We could further make rules for every unique branch of this tree, where each rule conveys a clear explanation of the factors and their values leading to some specific decision. As a precursor to learning how trees are trained, let's first look more closely at splitting. First, of note, basic decision tree implementations can only split a parent node into two offspring nodes. However, there are implementations that allow splitting into two or more offspring nodes. How splitting works first depends on whether a feature is categorical or quantitative. For categorical features, such as sex assigned at birth, the split is defined by the instance having one categorical value or the other, as can be seen here. And for quantitative features such as age, the split is defined by some threshold value for that feature. For example, is age greater than 25 or not? Next, let's look at how predictions take place within leaf nodes, depending on whether we are doing classification or regression, referring to the outcome being either discrete or quantitative respectively. As a classification tree example, let's say that we have the categorical outcome of sick versus healthy. Once the tree is trained, we look at the proportion of instances in a given leaf node that have one class or the other. In other words, the proportion of positives or negatives. And this determines the probability that the outcome is either positive or negative. Later, when we apply our selected decision threshold, this determines if our outcome prediction is either positive or negative class. Assuming a default threshold of 0.5, then the leaf node will predict whatever outcome was most frequent in the training instances that ended up in that leaf. So assuming red is positive class and blue is negative class, any instances ending up in this leaf node will be predicted as negative class, and any ending up in this leaf node will be predicted as positive class. While this example assumes a binary classification task, there are also multi-class implementations of decision trees available. Then there's regression trees, with a quantitative outcome such as height. Here, the predicted outcome at a leaf is typically the average of instance outcome values that ended up in that given leaf. In this illustration, we can see the distribution of training instance outcome values that ended up in either leaf. Also, we can see that for future predicted instances that end up in the left leaf node, they'll have a higher predicted outcome value than those that end up in the right leaf node. Next, let's look at a visualization of training and testing instances being passed through a binary classification tree that has already been trained. In this animation, training data is first passed through the tree, with the training accuracy reported below to be 100%. The two possible outcomes are represented by either green or blue circles. Also notice the leaf nodes of the tree are color-coded as blue or green, indicating the class prediction that will be made at those locations. Again here, assuming a decision threshold of 0.5. And next, the testing instances are passed through the same tree, yielding a testing accuracy of 89.7%. Now that we have an understanding of how decision trees work, let's find out how they're trained from scratch. Just like when making predictions, training a decision tree starts with a root node. But we need to decide what feature to place as our root decision node. To do this, we employ what's called Hunt's algorithm, which recursively finds a variable that best divides instances in the current node into subnodes, with maximally homogeneous outcome values. In other words, the feature that best separates one class from the other. This best variable is determined heuristically, where different heuristics can be employed to produce splits that are as homogeneous as possible. Some of the heuristics that have been employed in decision trees are listed here. You may recognize Gini and entropy as two of the criterion hyperparameter options from the scikit-learn implementation of decision trees that we mentioned in the last video. Once the best feature is identified, or the best feature and its split threshold if this is a quantitative feature, this process continues with more splits as the depth of the tree grows deeper. Splitting stops while going down a branch when certain user-specified stop criteria are met. For example, if some maximum tree depth is reached, or the purity of outcomes within a leaf node is reached, or some minimum number of instances in a node is reached. If none of these restrictions are in place, for example in a classification problem, splitting would continue until either all leaf nodes contain only one class, or when all leaf nodes include only one instance. Now let's look at a practical example of tree splitting on a simple example dataset. Here our target outcome is predicting whether a person has good or bad credit, and the features available in this small example include whether a given person has worked longer than 2 years in their current job, or whether they have missed any credit card payments. Remember that our goal in splitting is to separate instances in a parent node such that our offspring nodes will have the purest separation of one class or the other. And ideally, we want our classification to be successful in the fewest number of splits. So in this example, which of these two features should we split on? In this example dataset, we start with 3 instances with bad credit and 7 with good. If we split on the feature new job, this is what the outcomes in our resulting offspring would look like. Instead, if we split on missed payments, our offspring nodes would look something like this. So which of these options might you guess our homogeneity heuristic would suggest is better? In this case, the missed payment feature does a better job separating classes, where on the no branch, we have 6 good credit and only 1 bad credit, while on the right, we have 2 bad credit and only 1 good. So having picked missed payment as our first feature to split on, we might do another level of splitting if our stop criteria haven't been met. So let's see how our remaining feature might further improve classification. On the no branch of missed payments, we start with 1 instance with bad credit and 6 with good. If we now do a further split based on our new job feature, we get the following offspring nodes, with the no branch yielding perfect classification, which will now automatically become a leaf node, and the right branch with 1 bad and 3 good credit instances. Moving back to the yes branch of missed payments, we note that all the instances that ended up in this branch have the same value for new job. So there's no point in splitting further based on this other feature. So instead we would just make this a leaf node. Now that we have an idea of how splitting takes place, let's look at an example that illustrates how the decision boundary of a model changes as we add decision nodes to our tree. On the left, we have classification data with blue and green classes, and the features in the data that we're going to use we'll simply call X and Y that correspond to the values on our X and Y axes. On the right, we have our tree after the first split, which specifies Y having a value greater than 0.5. And so on the decision boundary, that would be this line right here. The yes branch of this tree corresponds to the red dashed area on the plot, here predicting class green based on it being the class majority. The no branch of the tree corresponds to this black dashed area on the plot, predicting class blue. As we continue splitting to a tree depth of 2, we've now added new decision nodes, here specifying x greater than 0.8, and here specifying x less than 0.3. So now this node, denoted by the red dashed box, has only instances with class blue in it. Thus, this automatically becomes a leaf node, and we're done with this branch. But this node, denoted by the black dashed box, still has a mix of the 2 classes, so we most likely want to continue splitting this branch. The next node, denoted by the yellow dashed box, only has instances with class green, so again this automatically becomes a leaf node. and the last node at a depth of 2, designated by this orange box, nearly has only one class in it. Technically, splitting could continue here. However, let's assume that our hyperparameters are set such that this node is sufficiently homogeneous and also becomes a leaf node. So at this point, if we continue to split the black dashed node further, we'll eventually get this. After reaching a depth of 5, notice that our decision boundary has gotten a good deal more complicated. And further, after reaching a tree depth of 10, we've generated a model with a very high training accuracy, which is doing a great job of separating our two classes. As a quick example, if instead we were creating a regression tree, it might look something like this. Within each node represented by boxes here, at the top we have the feature and threshold value used to conduct the split. So here, shell weight less than or equal to 0.168. Below it, we have the mean squared error, a regression metric we discussed in our last video. Within each node, this value represents the mean squared error between all instance outcomes within the node and the average outcome value of all the instances in that node. Ideally, we'd like to see this error dropping as we descend down branches of the tree. And upon inspection, this does seem to be mostly the case here. Below the error, we have the number of samples passing through each node. And lastly, the value here is the average outcome value of instances passing through each respective node. So at the top of the tree, note that all 3,341 instances in this training dataset passed through the root node. And these instances had an average outcome value of 9.958, as well as a mean squared error of 10.273. While down in the leaf nodes, the average outcome values in each leaf is quite different. So for example, a value of 12 point something, 14 point something, 11 point something, 9, 8, 7, 6, and 4. So we can see here how the different leaf nodes make higher or lower predictions about outcome value. Now that we've covered the basics, let's briefly discuss some of the key challenges for practitioners training a decision tree. First, how do we decide the best feature or respective value to split on? The sequence of features that get chosen can sometimes be different based on the homogeneity heuristic that we choose as our hyperparameter. Usually the best way to address this question is with a hyperparameter sweep, exploring this criterion as one of our hyperparameters. Another challenge is to decide when or under what circumstances we should stop splitting along a given branch. Again, this is something that can typically best be addressed with a hyperparameter sweep. Also, how do we address the potential for trees to dramatically overfit our data? Since a hyperparameter sweep picks hyperparameters that optimize a target evaluation metric, this can also easily lead to overfitting. Thus, for decision trees, it's very much up to the practitioner to be aware of possible overfitting and potentially restrict the values allowed for certain hyperparameters in the sweep that might easily lead to overfitting. This will be further addressed on the next slide. Next, related to overfitting, how do we train trees that are smaller or simpler? This can most easily be addressed by limiting the maximum tree depth parameter. However, an alternative approach to this involves post-processing a trained tree with pruning, which we'll discuss a bit more in a couple of slides. And lastly, what do we do about missing values, either during training or when applying a trained model to make predictions? We'll discuss this as well in a few slides. As mentioned, the next few slides are going to go a bit more into detail on 3 of the challenges mentioned, starting here with avoiding overfitting with decision trees. First, it's useful to reiterate that with sufficient features and a poor choice of hyperparameter values, it would be possible to train a model with leaves that contain only a single instance in them. And this would most likely be a perfect example of machine learning memorization rather than generalization. Fortunately, this type of extreme overfitting can be avoided by setting constraints on the possible values for the following hyperparameters. The first being tree depth, the second being minimum samples required for a node to split further, and the third being the minimum number of samples allowed in a leaf. Limiting all 3 hyperparameters can help to reduce overfitting in decision trees. However, another option is to employ tree pruning. This process removes targeted leaves and subnodes from a previously trained tree in a way that's designed to reduce tree complexity, but ideally improve or at least preserve prediction accuracy. Let's briefly talk about why pruning can be helpful. Specifically, decision tree splitting is a myopic and greedy process. I describe it as myopic or nearsighted because during each split, the algorithm can only consider the impact of one feature at a time. So in other words, it's seeking to pick the best split at that point in the tree without perspective of what will be the ideal split for the entire future tree as a whole. An analogy for this issue can be illustrated by this example of greedy decision-making while driving in traffic. Imagine that you are in this yellow car driving in a line of cars going 80 kilometers per hour, and your goal is to move down the highway as quickly as possible. Being myopic, you can only see the option of moving to the left, where there are no immediately visible cars, but with that option, you can't see the truck farther ahead driving at a much slower speed. And you also can't see that there are several cars ahead of the one directly in front of you. In this moment, the best choice might be to move to the left lane to pass the car in front of you. But as soon as you do, you quickly find yourself unable to pass the car, both due to the line of cars in front of it and the slow truck now in front of you. A similar kind of thing can happen during splitting while training decision trees. The tree makes short-term choices without being able to see the bigger picture. This makes decision trees less well suited to modeling multivariate interactions, as well as making them prone to overfitting. This is where pruning can potentially be useful. Pruning involves reducing the size of a decision tree by removing sections of the tree that are non-critical or redundant for the accurate prediction of outcome. Without getting into a lot of details, I'll mention that pruning can either be completed in a top-down approach with methods such as reduced error pruning, minimum cost complexity pruning, or minimum error pruning, or they can be completed in a bottom-up approach, for example using a pessimistic error pruning method. Moving on to our last challenge, let's briefly talk about handling missing values in a decision tree. Notably, the decision tree implementation in scikit-learn cannot handle missing values, so either features or instances with missing values will need to be removed, or the missing values would have to be imputed ahead of time. But some other implementations of a decision tree have been set up to handle missing data. For example, during training, a decision tree can simply ignore any data points with a missing value in the evaluation of potential splits. And during model prediction, when the model is faced with making a decision at a given node where the node's feature value is missing, there are a few ways we can handle this. One is the all-in approach, where the instance will be sent to the offspring node with the largest number of instances that ended up in it. This approach has been used by the cart implementation of a decision tree. Another approach is the weighted approach, where the instance is distributed to all offspring nodes with diminished weights that are proportional to the number of instances that ended up in each respective offspring node. This approach has been used by algorithms such as C4.5. And lastly, there's the random approach, where the instance with a missing value at the feature is randomly sent to one of the offspring nodes. This approach is available in some implementations of C4.5 and CART and has been used to achieve faster runtimes. At this point, hopefully you have some better intuition regarding how decision tree algorithms typically work. Before moving on to other tree-based algorithms, let's review some of the notable advantages and disadvantages of decision trees. The first advantage is that decision trees are pretty easy to understand as an algorithm in terms of how they work in training a model. This is likely because decision trees effectively mirror what might be considered human decision-making. Further, decision tree models are widely regarded as interpretable or transparent, which is the opposite of being a black box. Also, they are a fast and useful tool for data exploration, and they can flexibly handle different data types and outcomes. However, arguably they are better suited to classification than regression. They're also considered to be non-parametric, meaning that they don't assume any particular data distributions, and they're effective at conducting feature selection during model training, with the possible exception of doing so when there are complex, multivariate feature interactions. And finally, they train and make predictions quickly, even on very large datasets, in contrast with many other machine learning algorithms. However, as disadvantages, they are particularly prone to overfitting. While all machine learning algorithms are susceptible to overfitting, algorithms such as decision trees can be even more so, especially when allowed to train very deep and complex trees. Additionally, they are not regarded as being robust, meaning that even small changes in the training data can lead to a large change in the tree that ends up being trained, as well as the predictions those trees will make. Furthermore, decision trees are not ideal for regression problems. And as we mentioned, they're myopic, making them unreliable for capturing complex multivariate relationships, especially in data with a large number of features. And lastly, decision trees can have a bias towards categorical features with a larger number of possible categories when using Gini index as a criterion for the algorithm. Now that we're armed with the fundamentals behind a decision tree algorithm, let's next look at the concept of ensembles, with a particular focus on ensemble models made up of decision trees. First off, an ensemble is a group of models that are trained on the same task, where the point of this ensemble is to take advantage of the wisdom of the crowd of individual models. The wisdom of the crowd stipulates that a sufficiently large group of non-experts can make decisions that are often better than a single expert. This stipulation is based on the observation that an ensemble of models with similar generalization performance typically outperforms any individual model on its own. At a higher level, there are a few general types of ensemble approaches. The first is referred to as a hard voting ensemble, which is applicable to classification problems. Here, separate models trained on the same problem are utilized as a collection of voters, each submitting their class prediction. This majority vote is then translated into a class prediction based on some voting decision threshold. Notably, this ensemble of models can be generated from the same algorithm looking at the data in different ways, or from a variety of different algorithms applied to the same data. As we can see in this illustration, when a new class instance comes along, each model in the ensemble makes its own prediction, and then the class with the most votes becomes the prediction of the ensemble as a whole. A variation on this type of ensemble, used for regression problems, is that instead of voting, the predictions of the individual algorithms are averaged to yield the prediction of the ensemble as a whole. Yet another type of ensemble is called stacking. This involves training a meta-learner, or a secondary machine learning algorithm trains on the outputs of other models making up the ensemble in order to make a final prediction. And beyond these, we have the ensemble concepts of bagging and boosting, which we'll discuss in upcoming slides. So now let's examine a variety of tree-based ensemble learning algorithms of increasing complexity. Again, we begin with our understanding of a decision tree, which will be the algorithmic building block for all the other methods we're going to discuss in the remainder of this video. Introducing the concept of bagging is an important precursor to random forests. Then adding further randomness to the process of model training brings us to the random forest algorithm, one of the most popular machine learning algorithms to date. Next, we'll talk about the concept of boosting, and this will lead us to algorithms that utilize adaptive boosting, such as AdaBoost. And finally, we'll discuss the concept of gradient boosting, along with the concept of gradient descent, leading us to gradient boosting trees and some of the top performing machine learning algorithms currently in use, including XGBoost, LGBoost, and CatBoost. Again, all of these algorithms can be considered to be tree-based ensembles. Okay, so let's get started with bagging. Bagging is also known as bootstrap aggregation, or in the context of tree-based algorithms, it's also referred to as bagging decision trees. Bagging is an ensemble learning algorithm that trains independent classifiers on subsamples of the training data. This is done to reduce model variance and avoid overfitting. Bagging is a particularly useful strategy to combine with high variance and high capacity models such as decision trees. However, bagging can be combined with most any algorithm. Looking at the procedure for bagging, we start with some original training data and sample from this data t times with replacement. Sampling with replacement just means that after we sample, our subsequent samples are always taken from the entire original training set rather than subsequently sampling from what's left. Next, we train T models on the respective T data samples, typically using the same algorithm. Once trained, these models are combined as an ensemble which either vote for classification or take average predictions for regression. Bagging also offers the opportunity to generate its own internal estimate of model performance called out-of-the-bag error. This error is the mean prediction error on each training instance using only the trees in the ensemble that didn't have that respective instance when that particular tree was trained. Building further on the concept of bagging brings us to the random forest algorithm. As mentioned, random forest algorithms are a popular and highly successful extension of bagging decision trees. So first off, like bagging decision trees, the ensemble of trees is trained, each on a random sampling of the original training set. Random forests extend bagging simply by only considering some random subset of features in the data when conducting tree splits. Here on the right, we have another illustration of an ensemble of trees making up a random forest, where each tree has been trained on a subsample of the training set, and each split in each tree was made having access to only a random sample of available features in the data. Then this ensemble of trees makes predictions in the same way described for bagging decision trees, with a vote for classification or averaging for regression. The random forest approach works reliably well across many problems despite its simplicity. However, like with any ensemble, the major downside is the loss of overall model interpretability in contrast with basic decision trees. Next, we'll go beyond random forests to a slightly more complicated algorithmic concept called boosting. Boosting is an ensemble meta-algorithm approach for combining multiple weak learners into a single strong one. This approach is iterative, training weak learners sequentially, where, for example, a weak learner could be a one-level decision tree, which basically amounts to a linear boundary in decision space. So here we have our data set, and we have trained our first weak learner trying to separate out one class from the other. Boosting focuses on the errors made in the previous modeling attempt. For example, the red dot highlighted here was misclassified by our first weak learner. Each iteration, the weights or importances in classifying instances that were previously misclassified are updated. So in this example, our misclassified red data point has an increased weight going into our second weak learner training attempt. As a result, we train a second weak learner with a decision boundary that looks like this, now making sure to have properly classified this previously misclassified instance. This iterative process would continue on until we're ready to combine our weak learners into a single strong learner. Here we have an illustration of combining just two weak learners into a final strong learner. The best known algorithm using this type of boosting is called AdaBoost, which uses decision trees as weak learners. However, it should be noted that this type of boosting alone can easily be defeated by data that is noisy or that includes outliers. Next, we're going to learn about a more sophisticated form of boosting called gradient boosting. My goal here is to provide you with the intuition behind these algorithms' work in general, but for a deeper, more specific mathematical understanding, I'll point you to some great other videos later on. Gradient boosting, along with gradient descent optimization, are the essential ingredients of gradient boosting trees and other related algorithms. In contrast with boosting, gradient boosting iteratively trains weak learners, such as decision trees, not on different weightings of the original training data, but instead on the remaining errors, also known as pseudo-residuals, of the previously strengthening meta model. Here we have a simple illustration that might help explain what's going on here. Up at the top, this tree in a blue box represents the first weak model trained. At this point, our meta model just includes this first weak model. The small tree next to it represents the errors made by this initial weak model. The next iteration of gradient boosting trains a new weak model to predict the errors of the current meta model. Then our first and second weak learners are additively combined. This process repeats where each time a new weak model is additively combined to the strengthening meta model. We can think of gradient boosting as being another way to give importance to instances that are difficult to accurately predict, where each successive weak model works on the errors of all previous models combined as a meta model to try and identify patterns in the remaining errors being made. Intuitively, it should be no surprise that this approach can be very susceptible to overfitting, based on the enormous pressure on the algorithm to minimize error or maximize accuracy. A gradient boosting algorithm involves three key elements: a weak learner to train and make predictions. This, for example, could be a decision tree, but it could also be most any other algorithm that can be trained quickly. Second, we need a loss function that's going to be optimized. For example, this could be mean squared error if we're doing regression, or log likelihood if we're doing classification. And lastly, we need an additive model to iteratively add weak learners to our strengthening meta model in an attempt to minimize our loss function. To better understand what is meant by training a weak model on the errors made of the current meta model, let's look at a practical example using a regression dataset. Notably, this example will be a bit oversimplified in that it leaves out some weightings that we will introduce to the strengthening model later on. But I think it's the first step to understanding gradient boosting as a whole. In this table, we have our current example dataset, with our regression outcome, in this case, income, and two predictive features, including age and city, as well as an ID to indicate the unique instance rows. In training our initial weak model, our target is to predict the true outcome values in the dataset as have been replicated in this blue table, so we can see these values are all the same. So the first step in building a gradient boosting model is to train an initial weak model and use it to make predictions on our target data. So here we train a model using our two available features highlighted in red, and the respective predictions for each instance using this weak model are as follows. We can see that it's doing a relatively good job, but we're far from perfect. Next, we store our predictions with the data. We've copied our model predictions in blue on the right to this column labeled as Model 1 Income. In step 2, we use these predictions to get the prediction error for each instance, labeled as the residuals here in this blue column. So for example, 51,000 minus 53,500 is negative 2,500. At this point, these errors or residuals become the target outcome which we will try to predict in training the next weak model. And now we see that we have a new target outcome, which are the residuals of our previous meta model. In step 3, we build a new weak model to predict our new target outcome. Notably, the features we use to train the next weak model remain the same, in other words, age and city. And now with this new weak model, we get the following predicted outcome values in this new prediction column in blue. In step 4, we update the predictions made by our first weak model by adding these new predictions. So specifically, we're adding the predictions of our first weak model to our new predictions in order to get our Model 2 income. So for example, 53,500 minus 5,500 gives us 48,000. Note that on average, these new Model 2 predictions are closer to the actual income than for our Model 1 income predictions. This demonstrates that our strengthening meta model is slowly converging on making better predictions. At this point, we repeat steps 2 through 4, iteratively training and adding new weak models to our strengthening meta model. Note that as we go back to step 2, our new set of residuals is calculated as the difference between our true income and our new Model 2 income prediction. This process continues either until the error for all instances reaches 0 or until some other stop criteria are met. This could be some maximum number of iterations or some minimum of allowable error. So far, we've shown how to train individual models where our set of features that we'll call X here are being used to predict either our true regression outcome, Y, or the errors made by an existing meta model, which we'll label as E sub n. So our first meta model was just a weak model trained using features X to predict the target outcome Y. And our first model we'll label as M sub 0, capturing the relationship between X and Y. We represent the predictions being made by this model as Y prime, so the difference between our true outcome Y and predicted outcome Y prime is the error of our first model, E sub 0. Then we train another weak model, again with the same features represented by X, but now predicting the error coming out of M sub 0. Giving us our new model we'll call M sub 1 using X to predict E sub 0. Now we calculate the error of our current meta model, which is the difference between our true outcome Y and the predicted outcome of our strengthening meta model so far, which is a combination of M sub 0 and M sub 1, giving us the error of our second meta model, E sub 1. Then again, we move on to train yet another weak model predicting this new set of errors, which we call M sub 2. And this process continues until we've trained our last weak model, labeled here as M sub n, which again is using the features, labeled as X, to predict the previous errors. However, these models M0 through Mn just represent weak models. To have our final meta model, we have to have added them together along the course of training. And furthermore, after each iteration, it's typical to use some scaling factor or learning rate when adding weak models to our strengthening meta model. And lastly, while we could simply add each model to the prior one, we want to make sure that when we're doing so, we're ensuring that we're minimizing our target loss function for the overall meta model as it exists so far. And we do this using the gradient of the loss function, also known as the differential. So let's look at how we add these weak learners together. Like with the AdaBoost algorithm, boosting here refers to additively combining models together into a single new meta model, which we'll refer to here on as f sub n, which is a function based on our feature set of x. So after our first gradient boosting iteration, our current meta algorithm f sub 0 includes our first weak model m sub 0, and the error of this first meta model is e sub 0. After our second gradient boosting iteration, our meta algorithm f sub 1 adds the new weak model m sub 1 to the previous meta model, and this new meta model has error e sub 1. Continuing on to our third iteration, our meta algorithm f sub 2 adds the new weak model m sub 2 to the meta model from our last iteration, and this new meta model has error e sub 2. As we've seen, this continues on until we train a final weak model m sub n and add it to our final meta model f sub n, and this gives us the final error of our trained gradient boosting model, that error being e sub n. However, as mentioned before, it's typical to add a constant learning rate to downweight how much each new weak model will change the strengthening meta model. This learning rate, designated by the Greek letter nu, is a value between 0 and 1, often set to 0.1. This learning rate is multiplied by each weak model added after m sub 0. Choosing a smaller learning rate yields smaller, more gradual changes to the meta model and generally helps gradient boosting to better converge on a more accurate model. Let's further illustrate the potential impact of selecting a specific learning rate, which is a concept important to a number of algorithms outside of gradient boosting as well. More generally speaking, a learning rate is a weight applied to model updates as we seek to minimize the loss function of a model. If the learning rate is set too high, then each update to the meta model may lead to drastic updates, in turn leading to divergent behavior, such that it becomes difficult or impossible for the algorithm to properly converge on the minimum of the loss function, where the loss function on these plots is given on the y-axis. If the learning rate is too low, it might take a large number of meta model updates before the minimum of the loss function is reached. And ideally, we would pick a learning rate that is just right, allowing the algorithm to swiftly reach the minimum of the loss function, yielding a regression model with low error. Beyond learning rate, however, there is yet another parameter included when adding weak models to our meta model, and that is represented by the Greek letter gamma. Gamma is a pseudo-regularization parameter used to ensure minimization of the loss function of the current meta model when adding a new weak model. This parameter is similar in concept to the coefficients used to weight features in a linear or logistic regression model when training. However, unlike the learning rate, which is a constant applied to each new weak model, this gamma parameter is uniquely determined for each new weak model being added. For example, we can identify this gamma parameter, highlighted in yellow, for our initial as well as all following weak models added to our strengthening meta model. If we again visualize the loss function for our current meta model with all possible weights, in other words, different values for gamma, we want to find the value of gamma that gives our overall model the smallest error. Or in other words, the point where the gradient or slope of this loss function is minimized at or close to 0. This is the key element of this algorithm that makes it gradient boosting rather than just boosting. And so as we expand our meta model f of x each iteration, we'll minimize its loss function as new each weak learner is being added. So in this first equation, we weight our initial weak model by the gamma that minimizes our error. Then when adding our next weak learner, we multiply it both by our learning rate as well as the gamma that minimizes the error of f sub 1. And this continues, again adding a gamma that minimizes the error for f sub 2 until the end of our gradient boosting model training, where we select a final gamma that minimizes the error of our final model. So the next question you might ask is, how do we go about determining gamma for each weak model's addition? Again, the goal here is to pick the coefficient gamma such that the loss function for our current meta model is minimized. So we want to differentiate our loss function with respect to our current meta model, which gives us an equation for the slope or gradient of our loss function. In this animated figure, we have a model's loss function plotted on the left, and a corresponding linear regression model being fit on the right. In this example, our goal is to find the slope of our line, where the slope is represented in our left plot on the x-axis by the parameter p, and we want the slope that gives us our best model fit over here on the right, where the loss function of this line is given here on the y-axis as the mean squared error of the line. Note that in this example, the y-intercept of the line is assumed to be fixed at 0, so we're only trying to optimize one parameter, that being the slope. Of note, earlier, our loss function was simple for clarity, being set as the difference between our true outcome and the predicted outcome. However, 1/2 of the square of this difference is commonly used in gradient descent. Notice that as we change the slope of our line, we can see the errors across the loss function decrease. And as we make our way down this gradient, in other words, gradient descent, the slope of this loss function curve on the left approaches 0. When our slope is 0 here on the left curve, we know we've minimized the error of our regression model. So ultimately, we can get this gamma parameter value, represented in these figures as parameter p, either by solving directly for gamma with our differential equation equal to 0 using our calculus chain rule, and this makes the most sense when the math is simpler. Or alternatively, we can apply something called gradient descent, in particular if the math is more complex, which commonly happens especially when the number of parameters needing to be optimized simultaneously is larger. Because it's so important to many algorithms in machine learning, let's take a closer look at gradient descent. This is one of the most common optimization algorithms used in machine learning, applied in algorithms such as linear and logistic regression, neural networks, and deep learning. While in the last example, we only considered trying to optimize a single parameter, the line's slope, gradient descent can be applied to simultaneously optimize one or more parameters. As a slightly more complex optimization example than we had on the last slide, here we're again trying to fit a linear regression model. But now, instead, we have to solve for two model parameters, both our line's slope and the y-intercept. Gradient descent involves first-order optimization, meaning that it only relies on the first derivative when optimizing parameters. Also note that as an optimization algorithm, gradient descent has its own learning rate, separate from the one mentioned earlier to add weak models to our strengthening meta model in gradient boosting. Gradient descent usually employs a learning rate between 0.001 and 0.3. Gradient descent works by starting from some random guess for all parameter values, and then the gradient at that point on the loss function is calculated. And then the algorithm iteratively takes steps, updating the parameter values using some step size that is based both on the derivative, in other words, the slope of the loss function at that point, and the aforementioned learning rate. This is done repeatedly until we converge at the minimum of our loss function, which determines the best combination of parameter values, in this example, for its slope and the y-intercept. Of note, as mentioned in part 3b of this video series, in order for gradient descent to work effectively, all features in the data should have been scaled ahead of time. Hopefully this gives you some quick intuition for how gradient descent works. But if you want to understand it in detail, make sure to check out this great video on the StatQuest YouTube channel. While we're on the topic of gradient descent, it's useful to mention some of the major variants of this optimization algorithm. Before we do, I'll take this opportunity to mention this handy analogy for the process of gradient descent. You can think of it a bit like golfing, where you start far from the hole, where the hole in this case is the single or set of parameter values that minimizes our loss function. Starting from some point on the loss function curve with random initial parameter values, we have to decide how much to update our parameter values towards getting closer to the objective. When we're far away from the objective, we take bigger steps, because as we saw in the last slide, our step size is proportional to the gradient or slope at any point along our loss function curve. And as we get closer to our objective, we take smaller steps, since the gradient is slowly approaching 0. If we go past our objective, the slope of the gradient switches from positive to negative or vice versa, then we know we have to take steps in the other direction. I think this is a great way to better visualize how the gradient descent algorithm works in concept. So back to our gradient descent variants. The first variant is batch gradient descent. In this variant, all instances in the training data are used, meaning that this algorithm has a time complexity proportional to the number of instances. As such, this can be quite slow in very large datasets. Next, we have mini-batch gradient descent, which instead uses a random sample of instances to speed up the algorithm. This approach is less likely to converge on the true optimum, but it still works really well in practice. And furthermore, it typically yields better generalized models than batch gradient descent. And lastly, we have stochastic gradient descent. Here, each step is determined using only a single instance to estimate the gradient. In this visualization on the right, we can see batch, mini-batch, and stochastic gradient descent algorithms all operating to try and optimize model parameters, with batch having the most direct path down the gradient to the optimum, where the optimum is given as a red dot, and mini-batch followed by stochastic having increasingly sporadic and indirect paths towards the optimum. While stochastic gradient descent takes a longer path down the gradient, it can be faster overall as an algorithm, and ultimately yield the best generalized model. So now you hopefully have a somewhat better idea of how gradient boosting works to train a predictive model. But first let me point out that while different simple algorithms could be used to generate the weak learners in gradient boosting, decision trees are most commonly used. However, somewhat differently from what I've already explained, when using decision trees, the gamma parameter used to weight the addition of new weak models to the meta model is actually calculated for each leaf as its own individual predictor of outcome, rather than at the level of the weak model as a whole. This is slightly trickier to explain, which is why I covered gradient boosting a little bit more simplistically in the preceding slides. However, if you want a much clearer and deeper understanding of how gradient boosting trees work, I'd highly recommend this set of videos on the StatQuest YouTube channel. We'll end our discussion of gradient boosting and gradient boosting trees by mentioning some of the key popular implementations of this algorithm concept. The first is XGBoost, introduced in 2014. This variant includes a regularized gradient boosting approach, specifically including L1 and L2 regularization, as a modification to help prevent dramatic overfitting. Additionally, this implementation was designed with the option to be run with parallel computing, making it up to 10 times faster than basic gradient boosting. The next implementation of note is LGBoost, introduced in 2016. This variant uses gradient-based one-sided sampling, or GOSS, as well as exclusive feature bundling, or EFB. This implementation has been identified to run 7 times faster than XGBoost, and is considered to be a much better approach when dealing with very large datasets. And the last implementation we'll mention is CatBoost, introduced in 2017. This variant adds the capability to better handle categorical variables, and has been described as being a better overall performer in comparison to XGBoost and LGBoost. However, it's not as fast as LGBoost. We've reached the end of this closer look at tree-based machine learning algorithms. Let's quickly review the concepts and specific algorithms covered. First, we learned the fundamentals of decision trees, which offer a fast, simple, and interpretable approach to machine learning modeling. Next, we introduced the concept of bagging, and the role of bagging in bagging decision trees and random forest algorithms. These algorithms build upon decision trees, improving modeling performance and generalizability as part of an ensemble, but at the same time losing the ability to be clearly interpretable. Then we moved on to the concept of boosting. Here we saw how the basic boosting concept could improve modeling performance by combining weak models into a meta model, at the expense of an increased risk of overfitting, as well as a further loss of interpretability. And lastly, we covered the more complex concept of gradient boosting and gradient descent, used in algorithms such as gradient boosting trees, XGBoost, LGBoost, and CatBoost. These algorithms are typically expected to have the highest tree-based modeling performance, but at the same time are the least interpretable, and they still include risk of overfitting, even though this can be limited with the use of regularization. Thank you for joining me for part 5 of Machine Learning Essentials for Biomedical Data Science. In the next video, we're going to take a look at how some different neural network algorithms work, using some of the concepts we've learned in this video. If you enjoyed this video, please like and subscribe to follow my future content.